Thank you. Thank you everyone for coming. Throughout the last day, we've heard a lot about information security and the role that technology plays in our lives, our communities, and our world. We've heard how nation-state adversaries and threat actors have implications for personal privacy, civil rights, enforcement of our laws, and our national defense. These are heavy, important, and impactful topics. And this talk is not about any of that. For the next 50 minutes, I'd like you to join me on a journey of discovery for some good old, super random, family-friendly reverse engineering fun. I'm Jeremy Trimble. I'm an engineer, a hacker, maker, husband, and proud father of my two daughters, who were really the reason for all of this. In my day job, like many of you, I work in the InfoSec, reverse engineering, defense field at 26 Technologies. Our diverse team does advanced research in cybersecurity for embedded and mobile platforms, reverse engineering, vulnerability research, data analytics, machine learning, information operations, and combating manipulation. We support missions and customers across the US government and in commercial markets. And while I love my work and my team at 26, one thing they don't pay me to do is to hack speak and spells. So, please know that everything that you're about to see is my own work and opinions and not those of my employer. Our story begins a little over a year ago when my daughters noticed there was a problem with their speak and spell electronic toy. The speak and spell was first released in 1978, and there have been many updated generations and variations of the speak and spell over the years. There are some great links to the history later on in the presentation. But it occurs to me that maybe some folks in the audience grew up with one of these as kids, and others might never have seen one before. So, just to level set for everyone here, let's take a look at the original commercial from about 1980. Oh, hang on. Why not play? Stand by. Is this thing on? Okay, hang on. I think the sound guy walked away. We'll try it that way. Yeah, that doesn't seem to work. Okay, we'll do our best here. Man, 80s commercials were so informative. I couldn't even tell what half the Super Bowl ads were trying to sell me this year. Okay, so Texas Instrument got out of the business of making speak and spells a number of years ago. The version I'm going to be talking about today is a 2019 re-release put out by a company called Basic Fun that's made to look and sound like the original. So anyway, my daughters had found something was wrong with the keyboard. Either a key wasn't working, or was typing the wrong letter, which of course makes spelling hard. And they asked, "Hey, Dad, this is broken. Should we just throw it out?" And I said, well, let me see if maybe I can fix it, because I was really curious to get a look inside. I knew that the original speak and spells had contained some tech that was pretty cutting edge at the time that they came out. And I know that they'd been hacked and modified and circuit bent to do all kinds of things, used as musical instruments, and so on. And so I was really eager to get a look inside. And when I opened it up, womp womp. What the heck? Okay, old school speak and spells used to have some really cool tech inside, but I guess they don't make things like they used to. There's really not much going on inside this thing. Just a tiny circuit board that connects the battery, the speaker, and keyboard through the ribbon cable shown. There's a few passives and a big old epoxy blob that's partly covering up all the good stuff. But wait a minute. Okay, I do see one chip up here in the corner that's not under the epoxy block. It's a SOIC 8 IC, whose part number begins with 25, which I happen to know from previous experience is typically a NOR SPI flash memory. And the traces from that IC go under the epoxy block. I've still never figured out what's under the epoxy block, but the flash chip got me curious. So as a quick refresher, it's been a while since you worked with low-level hardware. The SPI interface is a 4-wire interface that lets chips on a circuit board talk to each other. Devices act in one of two roles: a master device, which starts the transaction, or a slave device, which responds once the master starts talking. SPI is used to talk between any number of different types of devices, like sensors, displays, or microcontrollers. And the flash memory IC in the speak and spell acts as a slave device, and the master is presumably somewhere under the epoxy block. SPI flash devices are really common in embedded and IoT electronics, and they have a de facto standard command set that's supported by most SPI flash ICs in existence. So this was actually the first picture I took in my teardown process, because I'd already desoldered the chip and was dumping it to file on my computer before I remembered to take a picture. And so using CH341A SPI Flash Programmer, I read out the entire contents into a file on my computer. The IC was an 8 megabit or 1 megabyte NOR flash from a company called Boya Micro, has the part number you see here, and it supports the standard commands that you'd expect from a SPI NOR flash. I was really curious at this point what was being stored on the chip. What could this be? I thought maybe it would have machine code, maybe it would have the actual word spelling data, it might have sound data on it, maybe storing high scores or something. And I figured if I could figure out what was stored on this chip, maybe I could change something about how the speak and spell works. I was excited. I'm like, all right, I bet I can figure this out right away. So at a really high level, here's a model of the speak and spell's electronics. The heart of the system is what I'm calling the processor, which takes inputs from the keyboard, drives output signals to control the display. Because it's under the epoxy blob, I still don't really know what the processor is inside. Maybe it's a microcontroller, maybe it's custom silicon. And the processor also has to talk to the flash chip over the SPI bus, otherwise the SPI chip wouldn't be there. And it also produces an analog signal that goes to the speaker to generate sounds. So, excited to find out what was on this flash chip I just dumped. I threw some typical reverse engineering tools at the data file. First up is strings. As most of you probably know, the strings command on Linux searches through any file, finds printable ASCII text strings, which is often useful because it can give you some clues about the intent of the file or its format. Well, strings found a lot of printable text in the file. None of it looked like human readable words. So, on to the next tool. Another classic reverse engineering tool, binwalk. Every reverse engineer loves this tool. You hand a file to binwalk, it comes through it looking for recognizable signatures, different types of data, certain file types, image formats, executable programs, zip files, whatever. And then it prints out a table of what it thinks it found, or even offers to extract that into separate files for you. Except it didn't find anything it recognized here. binwalk also has a mode where it calculates the entropy of the data at different locations in the file. Entropy is a statistical measurement of the randomness or unpredictability in the bits of a file. So data that follows a logical structure tends to have lower entropy, while data that's either encrypted or compressed tends to have a higher entropy. And sometimes that's helpful, but in this case it was kind of inconclusive. Up next was another one of my favorite tools for examining raw binary files. It's a lesser one called Hobbits, an open source tool from Millet Incorporated. Hobbits gives you a number of ways to visualize the bits of a data file, including the bit raster view, shown here where zeros are shown in a light color, the ones are shown in a dark color. Depending on how wide you make the raster display, you can sometimes see different patterns emerge in the data. You'll see Hobbits plots throughout the rest of the presentation today, and it ended up being pretty helpful in the end. But when I initially opened the file and saw what you see here, nothing jumped out at me, so on to the next tool. A hex editor. In this case, imhex. There are many great hex editors out there. Personally, I like this one, and they just had a release earlier this week. By default, imhex draws 0 value bytes as grayed out a little bit, which helps some of the structure to pop out here, but still nothing really made sense to me yet at this point. And so I admitted that, okay, this is probably going to be more complicated than I thought. And so, there the Speak and Spell sat on my workbench, completely non-functional because this flash chip wasn't even soldered to the PCB anymore for like 8 months. Now, folks who know me know that I'm a fan of the scientific method. You ask a question, observe, come up with a hypothesis or an idea, and do an experiment to see if you're right, and repeat until it makes sense. I think that reverse engineering is really just the scientific method by another name. The astronomer Carl Sagan once said, "Every kid starts out a natural-born scientist." Children start out full of boundless, sometimes uncontrollable curiosity, and they're on a mission to understand the world around them. As the years pass, some of us lose that curiosity and stop asking questions. But some of us never grow up. The truth is out there. All it takes is our creativity and persistence to find it. But the first step is to observe. Now, as humans, we're well equipped to directly observe some parts of the natural world through our 5 senses. Of course, when we're reverse engineering embedded systems, we humans have a pretty limited capacity to directly observe electricity, and when we do, it's usually unpleasant. We need tools to be our eyes and ears, to help us observe the things that we can't see on our own. And when you get stuck, it often helps to find a new way to observe. That's why I love electronics tools that help me observe and measure what's going on inside of circuits. It's like gaining a 6th sense. At least, that's what I told my wife so I could buy my next fun reverse engineering tool on eBay. DistrictCon EM100 SPI Flash Emulator. This is a useful tool for both forward development and reverse engineering. You connect one side to your circuit in place of the SPI Flash IC, and the EM100 acts as a virtual SPI Flash device, responding to read and write commands from the SPI master in your circuit. The other side attaches to your computer over USB, which allows you to quickly reprogram the contents of the virtual SPI Flash. It can emulate support for the de facto standard command set, as well as some chip-specific commands for hundreds of different SPI Flash ICs. And it also has a handy trace mode, which generates a log on your computer, the SPI transaction data to and from the virtual flash. The DistrictCon vendor's software doesn't support Linux, but I've never actually had to use it because there's an excellent community-supported open source project on GitHub that makes all of the EM100's features available in a handy command line tool. So our new experimental setup diagram looks something like this, with the EM100 taking the place of the SPI Flash in the circuit. And here's what it looks like in real life. I just soldered on a connector in place of the SPI Flash, connected that through a ribbon cable to a breadboard, break out all the SPI signals, and connect them to the EM100. Then I loaded the original file that I dumped from the original Flash IC into the EM100 in trace mode, crossed my fingers, and hoped that the Speak and Spell would start up normally. Sweet, okay, it worked. All right, so looking at the data from the EM100 trace gave me some new observations. I could see at the moment I pressed the on button that some activity started on the SPI bus. After an initial command that wakes up the chip, so I'd do several read transactions. First it read 2 bytes starting at one address, then it read 3 more bytes starting at a different address, 5 more bytes at another address, and then a whole bunch of bytes from a different address. So take a few seconds to observe the trace, see if anything interesting pops out at you. As you can see, the last bytes of the 5-byte read become the base address of the next read command. I thought that was pretty interesting, and as I looked at the rest of the trace, I saw that pattern repeated for every subsequent transaction. When the processor reads 5 bytes, the first 2 bytes are usually 00 CD, and then the last 3 become the base address of the next read command. Based on this, I was able to start drawing out a basic memory map of the bytes in Flash, like you see here. So far, I could tell we had this table of pointers that I called the offset table, which point to addresses of some long data blobs that appear at the higher addresses. There are also some bytes before the offset table that I just call the flash header. Although I'm not going to show it here, you should definitely check out the pattern language in the Impex editor, which lets you use a C-like syntax to declare and label data structures in your arbitrary binary files. Very handy. So next, I wanted to know what was in these data blobs. I'd heard somewhere that linguists generally think of speech as being composed of short units of sound called phonemes. And so I thought that maybe each of the data blobs was some kind of encoded phoneme data that got stitched together in order to say words. I set up an experiment where I collected the spy trace data, recorded the sounds coming out of the speak and spell, and then listened to the recording, marked the timestamps at which the different sounds were heard. And I overlaid the time intervals of the spoken phrases with the spy transactions across time, thinking I'd see multiple blobs being read for each spoken word. But I didn't. In fact, what I found was that the accesses were far more coarse-grained than I'd expected. It was more like each data blob corresponded to a single word or phrase. So hooked on phonemes didn't work for me. This turned out to be one of the many flawed assumptions that I had about the speak and spell. To confirm that each data blob was resulting in a word or an entire phrase, I came up with a confirmatory experiment where I took all the pointer values in the offset table and shuffled them around so they weren't at the same position in the offset table anymore. Then I tried turning on the speak and spell, and this was the result. Let's see. I call this Steve Martin mode in honor of a joke that I love from one of his stand-up comedy routines I listened to growing up, because that was what I did growing up, just listen to Steve Martin stand-up comedy on vinyl before it was cool, because it's cool now. Okay. Either way, go to the link so you can hear the joke and agree that that is hilarious. So now I knew that we have an array of pointers in the offset table, each of which corresponds to a data blob containing a word or a phrase, and I started to keep track of what each data blob said in a spreadsheet. I also wrote a Python script called live-trace to help simplify the output from the EM100 trace mode. So rather than showing every byte that got sent over the spy bus, live-trace would summarize it by just saying, hey, I looked up index X in the offset table and then read Y bytes of data blob from address Z. Also, each time that a different index in the offset table gets accessed, live-trace looks at my spreadsheet to see if there's a known phrase associated and prints that out too. This made it easier to help fill in new phrases in the spreadsheet as you play the speak and spell game. Throughout my project, I had more features to live-trace, like the ability to load in the original flash image, make modifications to it, and then easily throw that modified image over to the EM100 to play it on the speak and spell. So at this point, it was pretty evident that the sound data was somehow encoded in the data blobs. But what about the word spellings? If I could change the word spellings in the flash, I could add funny words or like make a whole new speak and spell game, like cybersecurity speak and spell. Now spell Ghidra. This would make a ton of sense, actually, because then the manufacturer could, for instance, create a speak and spell in different languages just by changing the data on the spy flash. So I was really hopeful that maybe the data blob included the word spelling data in addition to the sound. And conveniently, there was a really great experiment that could prove or disprove this idea. So in addition to the typical I say words, you spell them, that the speak and spell normally does, it has another mode called mystery word, which is basically hangman. It shows you a certain number of blank spaces for letters, and you have to guess all the letters in the word before you run out of guesses. And for this to work, the spelling data, if the spelling data is encoded in the data blob, then the speak and spell would have to read the data blob, or at least some part of it, or at least something, from the data flash before it presents the blank spaces back to you. But, alas, that's not what it does. So I conclude that the word spellings must be stored in another castle. Probably a castle that's covered in epoxy. All right, so the data blobs just contain the speech sound data. I wonder how that's encoded. So far, I have no information about how this speech data is actually encoded. So I tried the naive approach of just playing the bytes as a wave or a pulse code modulated time series, but that just produced noise. That wasn't too surprising, since in the meantime, I'd started reading a bit more about how the original speak and spell worked, and I was learning that it used a totally different concept that was pretty cutting edge in 1978, called linear predictive coding, or LPC for short. The original Texas Instruments speak and spells were built around the TMS 5100 speech synthesis processor, which was part of a multi-chip system used to implement LPC under the hood. The speak and spell and its history are chronicled in great detail at the link shown here in the slides. Also, shout out to the original speak and spell design team here, who took this cutting edge tech, used it to create a toy that became part of millions of childhoods. Linear predictive coding and algorithms for speech encoding more generally are a widely studied topic that people way smarter than me have been looking at for decades. But as a vast oversimplification, you should know that LPC tries to generate speech-like sounds by mimicking the human vocal tract. At a high level, the human vocal tract, shown on the top right, is composed of your vocal cords at the back of your throat, which can vibrate at a given pitch, creates a sound wave that travels through your throat and mouth. Your throat and mouth act as a formant filter, which has certain resonant frequencies that change as you change the shape of your mouth, enabling you to make different sounds that become phonemes, those building blocks of words. On the top left, you see the human vocal tract in block diagram form, and on the bottom left, you see the equivalent thing implemented as a digital signal processing system. You have a tone generator or a noise generator approximating vocal cords. That signal gets passed through a digital filter with variable coefficients that change over time. Parameters like the frequency of the tone, the loudness of the output, and the filter efficiency or filter coefficients are varied over time, usually in frames lasting about 20 milliseconds. The original TMS 5100 datasheet describes the implementation of such an LPC system in detail. And at the bottom, Table 1 shows how the parameters like the amplitude or volume, or the pitch, the coefficients, all of those get encoded into a ROM for each LPC frame. The TMS 5100 reads and decodes a new frame like this every 20 milliseconds using the parameters to program the excitation generator and the 10-stage digital lattice filter, which acts as the formant filter that eventually drives a D to A, which drives a speaker. It's worth pointing out that although the TMS 5100 is antique technology at this point, variations on linear predictive coding, like SELP and CELP, are still at the heart of modern audio codecs. So every time you make a phone call, your voice is probably being encoded and decoded using a technique based on this approach. After seeing all this, I started wondering if perhaps my 2019 Speak and Spell was also using a frame-based LPC encoding as well. I mean, after all, it sounded like the original Speak and Spell. Knowing that LPC systems encode parameters in frames and are read in and processed every 20 milliseconds or so, I thought it'd be interesting to look at the timing of how the data blobs were being read in over the SPI bus. The EM100 trace mode doesn't capture fine-grained timestamps within a single SPI transaction, so I needed a new way to observe the timing. So to better observe the timing of the data being read over the SPI bus, I attached a USB logic analyzer, shown on the left, and soon after I also attached an oscilloscope to the wire carrying the analog signal to the speaker, and brought the SPI clock and meso lines into the oscilloscope too, as shown on the right. On the logic analyzer, we can see that the data blob is read in as one very long SPI transaction. Also, there's a lot of idle downtime between bytes as they're being read over the bus. Also, there's a pattern to it. I always see it read 2 bytes, then 1 byte, then 2 bytes, then 1 byte, and so on. Here's the equivalent display on the oscilloscope. So with the blue and purple traces showing the same 2 byte, 1 byte pattern as in the SPI bus activity, but just on a different time scale here. It might be a little bit hard to see based on just the thickness of the trace lines, but trust me, it's there. The yellow trace is the voltage that's applied to the speaker. The series of different discrete values that you see show that this is clearly the output of a DAC, or a digital to analog converter, as you'd expect. And each of those values lasts about 100 microseconds in duration, which tells us that the output sample rate of the system is 1 over 100 microseconds, or 10 kilohertz. One more observation that's a little hard to show here, so I'll just tell you about it, is that the 2-byte, 1-byte reading pattern repeats 4 times for a total of 12 bytes, with the same timing between each read, but then a slightly different duration for the beginning of the next group of 2-byte, 1-byte reads. This was essentially a timing side channel observation that suggests something is happening on a 12-byte or 96-bit boundary. And sure enough, when we look at the bit raster of the sound blow-up data and frame it on 96-bit boundaries, finally there's some kind of pattern we can recognize. This bit 7 here is always set to 1 for basically the full duration of the sound blow. So from this, I conclude that our data is encoded in 96-bit frames. Of course, I don't know what any of those 96 bits mean, but it's a start. So I did a bunch more experiments. First, I did an experiment where I just repeated the same 96-bit frame over and over. Copied the first 96 bits in one of the sound blobs and pasted over and over to overwrite the rest of the blob data. And here was the result of that. All right, so this created a periodic signal on the oscilloscope. That part where the waveform looked like it was standing still, that's what it looks like when your oscilloscope is triggering repeatedly on a periodic signal. And you can actually see in the sample data the repeating pattern in the waveform of the trace on the right. Each frame contains the 2-byte, 1-byte read pattern for a total of 12 bytes read over the SPI bus. And also, each frame has 23 separate sample periods in the output. It's a little hard to see here, but trust me to count it. Remember that number, 23 samples. I'd also hypothesized that if this were an LPC encoding, then there should be certain fields in the frame which, when I change their value, should have a drastic impact on the sound. So like, imagine flipping a bit in the pitch parameter, I might expect the pitch to suddenly sound higher or lower pitched. So I did an experiment where I tried flipping or setting or clearing different bits within the frame. Many of the bit positions didn't have any audible effect, although some of the sample values I'd see on the oscilloscope would change. And some bits, when I changed them, would make the sound louder or quieter. And then one bit, that bit 7 that we saw earlier in the bit raster, when I cleared that, it just made the sound not play at all. So maybe I figured that's some sort of like keep going bit that tells the processor when the sound's over. Another experiment was to only set parts of the frame, so individual bytes or nibbles of the frame to 0, which mostly had the effect of introducing some distortion or making the sound quieter, but it was still intelligible. Yet another set of experiments was skipping every other frame, which made the sound get faster and higher pitched like this. My kids called that chipmunk mode. Or conversely, repeating each frame twice had the opposite effect, making the sound get slow and low pitched like this. Here's an example. So chipmunk mode was a hit with the kids, but also these findings made me start thinking that maybe this might not be an LPC-based encoding after all. Because in LPC, the excitation frequency is directly driven from a parameter encoded somewhere in the frame data. So I wouldn't have expected the pitch to change the way that it did. The speed should have just gotten longer or shorter, but without the pitch shift. So it's kind of back to square one. I knew the encoding was composed of 96-bit frames, but I only knew what 4 of those bits did. So what were the other 92 bits for? This really had me stuck for a long time. I went crazy about this for a few weeks. I tried starting from the periodic signal that I'd been able to generate previously and began flipping bits in the data blob and then trying to observe in a really granular sample by sample way what change that caused in the sound output in the oscilloscope. And knowing what I know now, They should have actually worked, but for some reason it was too complicated for me to keep track of what was going on this way. In the process, though, I became more and more convinced that the encoding wasn't LPC-based. At the time, I didn't exactly know why I thought this, but in retrospect, I think it might have been because I was noticing that there was essentially a causal relationship in the changes I was introducing. So when I flipped a bit at a certain point in the frame, it would usually mostly only affect samples that occurred later in the frame. If this were LPC, then just about every parameter change should have had an effect on the whole frame. I had to take a few weeks away from looking at this before taking a new approach. And the thing that finally actually worked was starting to generate my own bit patterns from scratch. So here I said to myself, okay, now I've got 96-bit frames, I know 3 bits affect the loudness, I know there's this keep going bit, and I got 92 other bits that I don't know what they do. Oh, and also that there's 23 samples per frame according to the oscilloscope output. Also, fun arithmetic fact, 92 divided by 23 is 4, even, which suggests that on average we're using about 4 bits for each sample in the frame. So I thought, let me just try generating some simple data patterns in the other parts of the frame. I added some code to live trace to generate my own sound blobs, filled in with bit patterns that I cooked up using NumPy. The code on the right shows one example test case where I generate a chunk of data with a particular bit pattern, set the loudness, and keep playing bits to something that I know will at least play the sound. So taking that same code from the last slide, here's what the resulting sound blob looks like as a bit raster. And playing that on the speak and spell gives you this output trace on the oscilloscope. And if we zoom in a bit, we can see that the waveform starts out at an initial value, then when the sound begins playing, it jumps up to a higher voltage, and steps down 4 times in one frame, stays constant for 7 frames, steps down 4 times again, until it hits some limit, probably the voltage rail of the output amplifier. Okay, that was interesting. Let's try a different pattern. Here I changed the 1111 to the first nibble of those bytes to 1010. And on the scope trace, yellow shows the new result, with the result from the test case 1 on the last slide being shown in gray, or maybe white on the screen here. We can see that this new test case starts out in the same position, but then the steps down are much larger, so it hits the negative limit much faster. There are in a bunch more test cases, I'll spare you the details, but this was the one when it finally clicked. So, setting the high nibble to all ones, and the low nibble to 0001 gives us this trace. You can see that the signal is now stepping back and forth between 2 discrete values. Okay, this makes sense now. If you remember that in 2's complement arithmetic, all ones corresponds to a value of -1, and 0001 would be a positive 1. So I concluded this looks like differential encoding, where we take the delta between subsequent samples and encode that. Okay, so knowing this, I tried to encode an example, a new sound for the first time. So that was a sine wave sweep, right? Just increasing frequency. So that was pretty exciting. Like, we're getting somewhere with this. So finally, after loads of black box experimentation, I figured out the frame encoding format, which is described here. Each frame is composed of 96 bits, aka 12 bytes, aka 24 nibbles, and 23 of the nibbles encode differential sample values, and that 24th nibble is what I'm calling the frame header, which has 2 fields. It has the keep going bit, which I mentioned previously, and what I was calling the loudness bits before. Actually, it turned out to be a per frame gain field called G, which I figured out through some other different experiments I'm not going to show here. The G value sets a power of 2 scaling factor that gets multiplied by the differential sample values of each step before they're added to the previous sample value. And the fact that the gain can vary from frame to frame kind of strikes a trade-off between the resolution and dynamic range of the signal when you decode it. So a relatively stable or quiet part of the waveform will be encoded with a small gain value, which gives you more effective bits of resolution, while the more dynamic or louder parts of the waveform get encoded with a larger gain value, which allows larger jumps in the signal to be encoded, but with less fidelity. It's worth pointing out that this decoding can be implemented efficiently with really minimal hardware, basically just a binary adder and a barrel shifter and digital logic, which is probably the point. On its own, I don't think that this encoding by itself is what creates the classic speak and spell sound. I think that the sound data encoded in the SPI flash was probably pre-processed before encoding to make it sound like the old school LPC-based speak and spell. By the way, if anyone in the audience knows of a name for this specific encoding implementation, I'd love to know what it is. I'm sure some document or data sheet somewhere describes an encoding like this. I've been Googling this entire time, but I've never found it. So now with what I knew about the encoding format, I wrote a script that could decode all the sound blobs from the original flash image into WAV files on my computer, which of course made filling out the rest of the spreadsheet pretty easy. And encoding new sounds isn't too hard either. So if you start from a time series with a 10 kilohertz sample rate, you just need to take in batches of 23 samples, or 1 frame at a time, compute the sample-to-sample deltas, and then pick an appropriate gain value for that frame, which is the main trick. The strategy I took was to just encode the frame 7 different ways, using all 7 possible gain values, and then picking the one that worked best as judged by an error metric. So the plots to the right show the results of encoding the same sound waveform with 3 different gain values. The blue trace is the original signal, the orange trace is the effective result after encoding, and the green is the differential sample increment values that actually get put into the encoded frame. So you can see that when the gain is too low, the encoded result can't move fast enough to catch the original signal effectively. When the gain is too high, the encoded result doesn't have enough resolution to match the original signal either. So we picked the Goldilocks gain right here, G equals 5 in the middle, where the error metric is the smallest. There are probably better ways to do this by optimizing the gain value across multiple frames at a time, but this has worked well enough in my testing. Okay, so now we can encode new sounds for anything that the speak and spell wants to say. We can't change the actual spelling of words, but we could, for instance, record a custom voice pack, replacing the classic speak and spell's voice with your own voice. Or, since we live in the future and deepfakes are a thing, and you can make anyone say anything, you could, for instance, replace the voice of the speak and spell with the voice of your favorite West Coast hip-hop artist. So I did, and today I'd like to introduce the Snoop and Spell. Snoop and Spell is a full voice pack upgrade that upgrades your 2019 Speak and Spell with its 1978 facade with all the hip-hop swagger of the early 2000s. I'm honestly surprised this didn't exist already because Snoop Dogg is just like everywhere right now. When I told my kids that I put Snoop Dogg's voice in the Speak and Spell, they were like, wait, you mean the guy from the Olympics? All right, well, maybe Snoop Dogg isn't your thing, but maybe you would like to record a custom Speak and Spell voice pack for a child in your life. All you need is a Speak and Spell, passable soldering skills, a cheap USB flash programmer, and some software that I'm releasing at the end of the talk to help you encode and compile your own Speak and Spell compatible flash image. In the course of preparing for this talk, I figured I'd better buy a spare Speak and Spell as a backup, so I purchased the one on the right in late 2024 from Amazon. I cracked it open, expecting to find my familiar flash chip, and oh no. Yeah, they changed the design. There's no external desolderable flash chip anymore. Wah wah. I haven't gotten very far with this new design yet, but I'd love to see someone else dig into it, and I'd be happy to discuss what I've found so far. In the meantime, don't worry, I'm still able to find plenty of hackable 2019 Speak and Spells used on eBay based on my purchasing experience, sample size 3. It seems like the ones with the lighter shade of blue on the exterior, as shown on the left, have the internals that I've described here today. I'd like to give a special thank you to all the following folks. Number one, to my daughters for letting me steal their speak and spell. To my wife for putting up with the constant speak and spell noises coming out of the workshop and for helping me to practice this talk. To Basic Fun, who didn't realize they were creating a reverse engineering challenge. To my coworkers at the Tube 6 Electrical Engineering Skills Group for being my first audience, even though they wanted me to talk about fault injection instead of speak and spells. To my friend Anna Stats for telling me about DistrictCon and suggesting that I submit this as a talk. And to the DistrictCon organizers who might have got more than they bargained for when they asked for bizarre reverse engineering talks. Also, very special thank you to Mr. D.O.G. himself for being totally cool with me putting his voice inside a speak and spell, and definitely like not suing me or anything like that, because he's super classy like that. Anyway, that's my talk. I hope you learned something, or at least put a smile on your face. Have fun, stay curious out there, and in our remaining time, I'd be happy to answer any questions. Yes, David.
What was actually broken in the first place?
Yeah, I think all I actually needed to do was just like reseat the ribbon cable.
There you go, over-engineering.
Yeah. But yeah, just got carried away.
How much of this did you explain to your daughters?
So they were really curious about it. A lot of this work was just for fun, something I was doing in the basement. I'd get up before the rest of the family on the weekends and go and try and figure out the speak and spell, and then they'd wake up and come down and say like, "Can we play Chipmunk Mode?" So, but they should be watching the live stream, so hopefully they caught all that. Yes.
So you played like a bunch of speech sounds. Did you try playing music out of it? Like, does that work?
Yeah, so I tried encoding some music. There's clips of Snoop Dogg songs on the Snoop and Spell. They're not super high fidelity, but and I think that's probably because one, the like weird dynamic range trade-off that the encoding does, and then also it's only a 10 kilohertz sample rate, which limits the amount of like fidelity you can have in the sound. Although there is a way to change the sample rate as well that I didn't talk about here, but you'll just have to check that out in the GitHub repo. I think we've got one more over here. Oops.
Did you ever find the word spelling lookup, like dictionary lookup, that said this word is spelled with this letters with these sounds?
No, I haven't. I'm assuming that must live under the epoxy blob. Like I said, I was really hopeful that it would be in the SPI flash, because it would make a ton of sense if it was stored there. You could create, many multilingual variants of the speak and spell, and I thought that would be cool to do. But no, it seems like, based on the mystery word experiment, that the spelling information has to be stored somewhere else. Oh, we've got some more over here.
What does your shirt say?
Oh, shoot. Yeah, sorry, I forgot to show you my shirt. Yes, so it'll be really easy to come find me if you want to play Snoop and Spell after this.
Can you give us one Snoop and Spell? Can you just like...
Oh, yeah.
Yeah.
All right, so when you first turn it on, it plays one of 4 random sounds that it picks, which I have different things, so we'll see what Snoop says this time. So okay, we're gonna let him ask us a word now. He's a rapper, so sometimes he talks really fast, so it can be challenging. All right, let's see. So there's a repeat button if you want to hear it again. Anybody know what that is? Let's just see. If you put in the wrong spelling. I tried to bring his personality to that. Any other questions?
When are you going to release the Snoop and Spell LLMs?
Yeah, so I thought another fun thing you could do with this would be basically make an LLM generate questions whose answers are the word spellings, and then make it generate the voice prompt for that, and play that, and then it would be like a trivia game. So somebody should make reverse engineering trivia, and then if you do it using an LLM, you won't know the answers ahead of time, so you can play it yourself too. Yeah, Vanya.
If you could look under the epoxy, is there anything specific you'd want to try going forward?
Like if I had like a new fiber laser or something. Yeah, I would be curious to see what it is. I expect we might find some like bare silicon stuff underneath that we may not necessarily be able to read the instruction code out of or anything, but maybe we could. So yeah, I would totally try it. I was trying to limit how many speak and spells I had to buy for this.
Did your daughters actually get any use out of the Snoop and Spell, or was it more of a novelty?
They thought it was funny for like 30 seconds. Yeah. Oh yeah, I could do Chipmunk and Spell. Chipmunk and Spell I think they actually liked better than Snoop and Spell. But conveniently, with the code on GitHub and your own EM100 SpyFlash emulator, you can do all of these modes by passing different command line switches to live trace. Yes, Zach, these aren't plants.
Do you think we could take a low-cost microcontroller, like an RP2040, and then modify the case slightly, and then have the RP2040 like emulate the SpyFlash somehow? And then that way you could easily reprogram codecs instead of having to take the screws out every time, you know, and then sew a gate.
Yes, yeah, we can do all that. You could probably, I think if you keep the keep going bit set, you could kind of make the processor play forever too. So if you wanted to just have it be encoding a constant stream that goes on forever, or like stream music onto your RP2040 or whatever you want. Go wild with the people. All right. Thank you, everyone.